So, we're back to this talk series after GDC break, and today I want to talk about the plugin system in the engine. So the plugin system is quite recent system. It's a bit more than a year old or something like that by now. And the purpose, the sort of goal behind the plugin system is to allow Stingray to be extended in various ways, and to do that without requiring access to source code. So our customers that are using Stingray should be able to extend it in various different ways without having to have access to all our source code. And it should also be, the extension should also be as decoupled as possible, so that the extensions are not deeply dependent on the way we've implemented our systems in the engine, so that we can change our implementation in various ways, which we might want to do in the future as we add more features or improve the performance of a system. And those changes shouldn't really affect the plugin. So plugin writers shouldn't have to rewrite their plugins with every version of Stingray. So it's another goal to keep the plugin stable and the plugin API stable across different versions of Stingray. And we want this to be both forward and backward compatible. So what that means is that if you've written a plugin for a specific version of the engine, it should work with future versions of the engine, but it should also possibly work with older versions of the engine. Just as much as compatibility as is possible, so that we don't force plugin writers to constantly rewrite their plugins. And the main reason for having a plugin system at all is to be able to move concepts out of the core engine. So we have some concepts in the engine right today that are pretty game specific, that I've talked about before, and that you really can argue that they don't really belong in the core engine itself. For example, we have things like splines, spline support, which some games might be interested in using splines, BSC splines, which is what we have support for in the engine. Some games will not be interested in that at all. Some games will want to use something completely different. And just having one particular system hard-coded in the engine and only supporting that means that a lot of games will not use this feature, and then it's just an unnecessary feature, and a lot of games will want to use other stuff than these particular splines, and they can't if we don't have an extensibility system. And we can't just put everything that everybody wants into the engine, because then it will become a huge complex beast that is impossible to work with. Other such concepts that are really game specific are a lot of AI stuff, like navigation, which is already a plugin today, but also stuff like finding objects near you, different kind of behavior machines, like behavior trees maybe, or state machines, or whatever you want to do to use to drive your AI, which is pretty game specific. Not all games will have a cover system, for instance. So all these game specific systems shouldn't have to exist in the core engine. It should be possible to extend the engine with whatever systems you need. And the goal is also in the long run to have some kind of asset store or some central place where you can download these plugins from and use them. So it should be able to package a plugin up as sort of a binary package and put it somewhere. I'm only talking about the engine side of plugins in this talk. There's a corresponding tools sign where you can extend the tools with HTML5 stuff. Oh, I guess, Jonathan, you're talking about the HTML5 plugin that gives you a HTML5 interface inside Stingray for doing UI inside the engine with HTML5. which is another great example of a useful plugin. We have a lot of plugins already, and a lot of our existing systems have been moved into plugins. Like we have the Human Air Key plugin, we have the navigation plugin, HTML5 plugin, lots of interesting examples of plugin code already. So the interface for writing a plugin is based on C rather than C++. The engine, most of the engine is written in C++, but for the plugin interface we decided to use C. And there are a number of reasons for that. The most important one is that C has a stable application binary interface, which means that it doesn't really matter which compiler you use or which particular compiler flags you have set for that compiler. The binary interface, that is the way that one function calls another, and the way that structs are laid out in memory and so on, is the same across different compilers and different versions of the compilers and so on, which means that you don't have to care about compiling your plugin with exactly the same compiler and settings that we use, which would be a great problem if you have to do that. C++ has name mangling, so when you compile a method in C++, the name of that method isn't just the name of the method itself, because that would lead to collisions, and C++ has overloads. We would get methods linked with the same name in the linker. So instead, the name is mangled, and various characters are added to the name to represent the parameters that the function takes. And this name mangling is done differently by different compilers, which means that there's no standard way of calling C++ functions between compilers. So for these reasons, we use C rather than C++ in the interface. And it's also a smaller, another reason for using C rather than C++ is that when you're using C++, you kind of have a wider design space. And by that, I mean that in C++, you're always faced with a choice if something should be a member function or a freestanding function and something else. So you have a bigger design space for designing your API. You can define them in a lot of different styles, and that can lead to problems, because then you might end up with different APIs using different kind of styles, which makes the interface sort of inconsistent. So, but C has a smaller design space. Everything is functions. You have only a few basic types and so on. So that also makes it easier to design a stable API. The plugin interface is based on a single function. So it's a single function that the plugin exposes to the engine. It's called getPluginAPI. It takes an unsigned identifier, which is an ID of an API that we are querying for, and it returns a void pointer. But that pointer is actually pointed to a struct, and the struct has a number of function pointers in it. And these are the function pointers that define this API. So, for example, each API has a specific ID, and it has a specific struct that defines the functions in that API's interface. For example, there's one general API for plugins that we will see later that has functions to call when the plugins get loaded, when the plugin gets unloaded, and so on. And this single function is really the only thing that is shared between the engine and the plugin. So we don't try to share other parts of the engine with the plugin. For example, in the engine, in the Stingray engine, we have a lot of, well, not a lot. We have, compared to other engines, we have a few collection classes. We have, for example, our array class and our vector class and our hash map and so on. but we don't try to share our implementation of those clauses with the plugin. Instead, the plugin, if the plugin wants to use some kind of vector representation, the plugin can define its own. And the reason for that is that we want the contact surface between the plugin and the engine to be as small as possible. Because if we sort of shared the implementation of the hash map, for instance, then that would mean that we couldn't really change that implementation without breaking all the plugins. So that would lock down the engine and lock down the kind of changes and optimizations that we can make in the engine. For example, we may discover that our hash map implementation is not the best one, and we can change to a different hash and maybe a different binary layout of the hash map, and that makes it much more efficient. If we're sharing that implementation, sharing the details of that implementation, we can't really do that. So our goal is always to have the contact surface between the engine and the plugins as small as possible, because that allows us design freedom. So the plugins expose this function getPlugin API, and they are required to implement one API. They can implement more than one API if they want to, but they are required to implement one API, which is called the plugin API, and it has a specific ID, which is the plugin API ID. And when this getPlugin function is called with that ID, it will return a struct that looks something like this. It has a getName function that returns the name of this plugin. It has a loaded function, which is called by the engine when the plugin is loaded, and that has a corresponding unloaded function when the engine unloads this plugin. So the loaded function can perform necessary setup of the plugin, and the unloaded function can tear down the same stuff. And then there are a bunch of other callbacks too in here. And finally, we have at the end of the API, we have a bunch of reserved function pointers, so that we can, and these are all initialized to 0, but they might be used in future versions of the engine. We might add additional functions to this API. So I'll talk a bit more about that later when I get into the versioning, how we use this. But this plugin API defines callback functions that will be called by the engine at specific points in the engine execution. So I already talked about loaded, unloaded when the plugin is loaded, but there are corresponding callback functions called at other points, for example, when starting the game and so on. So the plugin can implement these callbacks and return pointers to them in this struct for all the sort of interaction points that this particular plugin cares about. And if there are things that this plugin doesn't care about, for example, the plugin might not need to do anything when it's unloaded, then it can just return null. If it doesn't have anything to tear down, it can just return null in this value. So this is how the engine calls the plugin. The engine loads this function, getPlugin API, using the standard DLL loading scheme, and then it calls that function to get this struct with the function pointers defined in the plugin API, and then it calls its different callbacks at the necessary points. And calling the other way, calling from the plugin to the engine, works the same way. So when the plugin wants to tell the engine to do something, for example, spawn a unit or create a new world or so on, it uses a very similar mechanism. The engine has a function similar to the getPlugin API. The engine has a function called getEngine API that works exactly the same way. You pass in an identifier that identifies a specific API in the engine, and then you get back a struct pointer with functions to call back for calling that API. And this function, this engine function, is actually passed to the plugin when it's loaded. So you see, if you look at this loaded callback, it has a parameter which is the getEnyin API function. So the Enyin passes its function down to the plugin, and then the plugin can use that to call back to the Enyin to get the different interfaces supported by the Enyin. So the Enyin has a bunch of such interfaces. There is a Lua API for doing stuff with Lua. There is a data compiler API for compiling data, an allocator API for using the Enyin's allocator, and so on and so on. And all of these are defined in a file called plugin API that sort of defines the API for the Enyin. It has a list of all the different IDs for the different kind of APIs supported by the Enyin. For, you see, there's a lot of stuff here like raycasting, doing stuff with the world, doing stuff with meshes, and so on and so on. And then you have all the structs here defined. Plugin API, which is the API implemented by the plugins, and all the different callbacks. Then you have the Lua API for doing stuff with Lua, adding new functions to the Lua interface, and so on, and so on, and so on. This is quite a big file since it has all these different Enyin APIs. And if you're writing a plugin for Stingray, all you need is really this plugin API file. It has all the definitions you need in order to call these different APIs. So we can look at an example of a simple plugin. This is an example that comes with the Enyin. It's called the simple plugin because it's kind of the simplest possible implementation of a plugin. It's just 80 lines of code. That's the entire plugin. And it exposes this get plugin API function, which is this is just exposed for dynamic linking. I'll talk a bit more about dynamic and static linking of plugins later. But anyway, this getting plugin API function compares the ID that is passed in. If it's equal to the plugin API, that's the only API that's supported by this plugin. It sets up this struct and initializes the callbacks that it will use: setup game, shutdown game, and get the name of the plugin. Then you have the implementation of those functions here. So you see here, setup game gets this get Enyin API function. It uses that to fetch the Lua API and the plugin manager, and then it adds a new function here, which is just a test function. Adds that to our Lua API, adds a new Lua class called simple plugin, and adds a function called test in that plugin. And corresponding shutdown removes that class. Get name just returns simple plugin. And then you have there's another more complicated test here, the test calling between different plugins. But in this simple test just adds this test function to the Lua API, and it's just an add. It just takes two numbers and adds them and returns the result in Lua. That's really all there's to it. So a plugin doesn't need to be more complicated than this. So versioning of plugins. As I said in the beginning, the intention of the plugin API is to be both backwards and forwards compatible. So plugin DLL should be possible to use a plugin DLL both with a newer version of the Enyin and an older version of the Enyin without having to rewrite the DLL. So how does that work? Well, to begin with, the plugin API is locked. We don't change or remove functions in the structs that we return. So with this API here, let's see which one it is. This one, right? So in this this struct here, for example, this API struct and all the other API struct will always have these functions at these positions in the struct in all future versions. We locked this in a specific version. We locked this down. It was mutating a bit before, but from version 1.8 of Stingray, this is locked down to always have these function calls in these places. And the only place where we add new functions is at the end. So in that, if you remember, we had this reserved area here for expansion of the API, and there we can add new functions in future versions of the API, but we don't modify the existing functions. Unless we really need to. If you really need to make big changes to the API, like we need to remove a bunch of functions or change the parameters, we can actually do that by creating a new API. So in that case, we would take our existing Lua API. We would still keep our existing, if we needed to do that with the Lua API for example, we would keep the existing Lua API and we would just add a new one called Lua API version 2 or something like that. And that one could have a completely different struct if we need to do that. So we have a mechanism for doing that too. Making big changes without the old API would still be the same, and it would still be returned if you called it with the old API ID. So how this would work in these both forwards and backwards compatible modes is, for example, if we have an old DLL and a new engine. In the new engine, the old functions will still be in the same location in the struct with the same parameters, because that's our requirement. We've promised that we won't move these functions, and we promised that we won't change their parameters. And this means that the old DLL can still continue to use them. When the old DLL requests the structs, all these functions that it wants to use will still be in the same place and still use the same parameters. So it can continue to use them without any modification. There might be new functions in the struct that is returned, but all those new functions will be in the reserved area, so the old DLL won't use them. It won't look at the reserved area. So it doesn't disturb the old DLL in any way. It can continue to function as before. If we have the other situation, a new DLL running with an old engine, well, the new DLL, there might be new functions in the API that only exist in the new version of the engine, and they will be in the reserved area. So the old engine always initializes all the pointers in the reserved area to null. So when the new DLL requests the interface from the old engine, it will receive back a struct, but some of the function pointers in the struct will be null because those functions didn't exist in that version of the engine. And the new DLL can then check if the functions are available or not by checking the function pointers against null. And if they are null, the new DLL can sort of do something else instead of calling those functions in order to keep compatibility with old versions of the engine. Of course, if the new DLL is absolutely dependent on some new functionality, it won't work with old engines in that case, but that's a situation we can't really solve. But with this approach, we can at least make it possible to write DLLs that are compatible with old versions of the engine, as long as the DLL does the appropriate thing and check which functions are available. So that's how we get both these forms of compatibility, which is really nice. So in addition to the other APIs we support, one of the APIs we support is the C API, or we call it the C API, and it uses an ID which is called the C API ID. And the idea behind the C API is that it should expose the same functions as we do in our Lua API. So this is really the interface for writing gameplay in using C or C++, whatever you want. Of course, you can write your DLL in C++ as well. Just use the interface function as extern C function, and it works perfectly. So this API allows you to write all your gameplay code that you used to write in Lua. You can write it in C instead, and you can keep it in a DLL, so it doesn't need to interface directly with the engine. It can just be in its own separate DLL and be compiled on its own. And just as the Lua API implements error handling, if you call a Lua function and you pass the wrong parameters, or you send things over the wrong, do something bad in Lua, we don't crash the application. Instead, you get the Lua error, and you can sort of handle that error and do the appropriate thing, in Lua. So it doesn't bring down the entire application. And we do the same thing in our C API. So that's another reason for using it. I mean, you could write your gameplay code directly against the engine interfaces instead of using the plugin interface. As long as you had source access, you could just add to the engine. The problem with that is you wouldn't get this version compatibility. You'd be much more dependent on the actual engine implementation, which means that it could break in the future if the engine implementation changes. Also, it requires source access, and you don't get error handling. But with this C API, you actually get error handling. So if you call it with bad arguments, instead of just crashing the engine with an access violation, you actually get an error message. And in the C side, we implement this error handling with long jump. So if we encounter an error situation, a null pointer or some other bad data in a call to a C API function, we will long jump out to a safe place so that the gameplay code can sort of handle that error. Yeah, and as Dan says, the C API is quite a new addition to the plugin interface. We implemented the other APIs first, and then we sort of added this C API later. So the C API is currently not locked down. The other interfaces are locked down for version 1.8, but with C API we still reserve the right to change it in future versions. So it doesn't follow this backwards-forwards compatibility rule yet. But we will lock it down and sort of freeze it in some future version, and then have backwards compatibility and forward compatibility for this interface too. So one interesting thing to note is that as we are implementing the C API, we're actually rewriting our Lua API. The Lua API used to call engine functions directly, but we're now rewriting it so it's based on the C API. So we really only have a single API interface to the engine, which is the C API, and then we have a Lua wrapper layer on top of that converts it into Lua syntax, sort of. So we only have a single API now. And you could also add other languages, bindings for other languages on top of this C API. And I know Stefan has done that for Python, for instance, done a Python binding on top of the C API as part of his Hackday projects, which is kind of nice. You can extend the engine with other languages. So I said a little bit about static and dynamic plugins. We can actually, by default, the idea for plugins is to link them dynamically, so you can have a DLL and just load it or not. But we can also link plugins statically, link them into the main engine binary. And to do that, to do static linking, we just take this get plugin API function and we put it in a list for all the modules that we link statically, and we put it in a list of our statically loaded plugins. And apart from that, everything works the same way. Note though that in this case, if we're linking statically, we need each of these get plugin functions to have a different name, because otherwise we would get name collisions in the linker. So you can see how this is done here in the plugin example I just showed you. Wasn't it called oh, it's called plugin. Let's see. Yeah, you see here if we're so this is the function that gets linked in. If we're doing static linking, we just add this to the list of static libraries. And if we're using dynamic linking, we have this function that we export. If we link statically, we don't export this function because then it would collide with other functions from other plugins. Static dynamic linking. So currently we only use dynamic linking on Windows, and we require static linking on the other platforms, iOS, Android, PS4, and Xbox One. So that means that in order to use plugins on these platforms, currently you need source access because you need to be able to link statically. We're looking into adding dynamic linking to iOS and Android too. On PS4 and Xbox One, you're not allowed to release with dynamic linking. That might be the case in iOS too. I'm not sure. I think it might be okay now. But anyway, so we probably will keep the static path anyway for platforms that require static linking. But we're looking into adding dynamic linking support to other platforms. It's useful during development too. Even if you can't release with dynamic linking, it's useful during development because you can reload your plugins, as I will mention later. So cross plugin calls. Yeah, in addition to requesting APIs from the engine, you can also request APIs from other plugins. So you can ask, is there any other plugin that supports this particular interface? And there's a function for that called getNextPlugin API. So you can call that and pass in an identifier, and you also pass in the pointer of the previous API. So this can be used to enumerate if you have multiple plugins implementing a particular API, which could be a situation. For example, say that you have a plugin API for drawing trees, then you could have multiple tree drawing plugins implemented into the engine. So calling this with null here would give you the first one, and then you would pass in the first one here to get the second one returned, and so on. And that way you can enumerate all of them. And in fact, this example that I showed you earlier actually has an example of this too. So that's this test cross plugin call function. So it adds another Lua function for testing a call across plugins, and it gets the plugin manager API in order to get this getNextPlugin function. It calls that to get a graph API, which is just it's an interface that is implemented by another sample plugin called the bigger sample, which you can look. All of these are online, are sample plugins. So it gets the interface from that plugin and can then call that plugin directly to do something. So in this way, different plugins can cooperate. The implementation of the plugin system is quite simple. We just scan. We have some directories that we scan for plugins, like some directories where you can put plugin DLLs. And we scan those to find plugin DLLs that match certain patterns. We require it's just a match on the name to see if which DLLs implement plugins. And then we just code load library. This is on Windows. Load library on the path of the DLL, and we call getProsAddress to get the address of this getPlugin API. And then we call this loaded function, which is a part of the plugin API. And then we continue to, at specific points in the game, like start game and stop game, we call into our list of loaded plugins if they have implementation, callback implementations for this these things. So one issue that sort of comes up when you start doing this is what are the good interception points for a plugin? Like, at what points in our code should it be possible for a plugin to get a callback? And I mean, typically you start with something like this: a callback when the plugin is loaded, a callback when the game is started, maybe a callback at the beginning of every frame, and so on. But you can sort of go down a tricky path with this, because there are lots and lots of places where a plugin might want to be called. For example, maybe a plugin wants to be called after animation has completed, but before we run physics. Or an animation wants to be called after physics, but before particle effects are evaluated. So how do you do that? Do we insert like 1,000 different callback points at every different point in the engine? That's not a super good solution, because for once it will look really ugly to have, like, at every point in the engine there's lots and lots of plugin callbacks. But more dangerous than that is that it sort of locks down the design of the engine. If we have a callback point that is like, well, this is a callback after animation but before physics, then that sort of requires us to always do animation before physics. Maybe we want to do them in parallel at some point in the future, but now we have this weird callback that requires us to serialize them. So, and I don't really have a good solution to this. I mean, right now we have sort of tried to keep the callback points minimal, but the situation always arises when you start to think about, like, well, maybe this plugin would like to want the callback at this specific place. And I'm not entirely sure what to do about that. Like, what is a good solution to this general problem with plugins? How do we allow them to patch anything without it becoming a huge mess? So that's something to think about. We support hot reloading for our plugins. So the plugins can be reloaded while the game is running. And you can use this if you're working on a plugin. You can sort of just recompile that plugin's DLL and do iterations over it without having to restart the game, which can be really nice. It's especially useful when working on gameplay plugins. You can sort of tweak the gameplay, change parameters, and recompile it without having to reload the game. So the procedure for hot reloading is not super complicated. We look for changed DLLs. So in these directories where we load plugins from, we scan them to find modified DLLs, versions of our plugins. And if we find a new DLL, a new version of a DLL, the date has changed of one of these DLLs, one of our plugin DLLs, we call a function in the plugin API. It's called start reload. And that is to give the plugin a chance to save its state. So it might be that this plugin has some state that it cares about, and it wants to preserve that state. For example, a plugin that draws trees might have a state that is the position of every tree and the kind of tree that is spawned at every position. So we call start reload, and it returns a state which is just a memory buffer, just a big blob of memory. Whatever the plugin wants, it can just put down into a single memory blob. And then after we've called that, we unload the old DLL. So this call happens with the previous version of the DLL, not the new version. So the previous version can save its state. Then we unload it and we load the new version. And then with the new version, we call finish reload. And we pass in the state. So at this point, the new version of the plugin can sort of restore its internal state from this saved state buffer. So because the new version might have different struct layouts, different memory configurations, and so on, so it might not be it might not look exactly the same in this new version of the DLL, but they share this same serialization of the state. So that's just if you want to preserve the state. If you don't care about preserving the state in the plugin, you don't need to implement this start reload and finish reload functions. In addition to this, there is a lot of stuff to deal with stupid Windows file locking, because as I'm sure all of you know, Windows have a tendency to lock files, and then it doesn't let you write over these files, which can be really complicated, much more complicated than you would think when you want to do stuff like reloading plugins. Because when the game has loaded one plugin, Windows consider that file locked. So if we want to build a new version of that plugin, we can't save it because we can't overwrite the old version, because Windows keeps that one locked. We can't delete the old version either, so we can't delete it and then write a new one because it's locked, so we can't delete it. And the same applies to the PDB files, except with the PDB files it's even more tricky, because the debugger can lock multiple PDB files. So if we've compiled the plugin, the debugger can lock the PDB for that version. Then we reload and load a new version. The debugger can have both those PDBs locked at the same time, which is really annoying. So our solution to this is just to implement a pre-build step in the code in the project that builds the plugin. So we have a pre-build step that first renames the DLL, the existing DLL, to the same name but with old prefixed. And this is actually safe, even though the file is locked. Windows lets us rename it in the same directory, which is nice. We can do this. And then we try to rename the PDB, and which might fail because the old PDB might still be locked by the debugger. So then we have a safeguard to delete. If we can't rename this PDB, we try to delete it instead. And then we build the new plugin DLL. So by doing this, we sort of work around the Windows file locking issues, which is annoying. If Windows had like proper inode implementation, we wouldn't have to do any of this. So as I said in the beginning, this covers the Onion plugins. We also have an editor plugin system that allows you to extend the editor with new functionality, new HTML and JavaScript files. And these are kind of separate systems. So if you want to make a plugin which extends both the Onion and the it should be both the Onion and the editor. Onion and the runtime are the same thing. But if you want to do something that extends both the Onion and the editor, you have to do both these kinds of plugins. You have to do your Onion plugin for adding the functionality to the runtime, and then the editor plugin for adding the functionality to the editor interface. So that is really all I had about the plugin systems. Are there any questions on this? So Jonathan was typing something. All right, good. Right, if there aren't any questions, I'm all done, and we'll talk again tomorrow with the next part of this series. Thank you.